Hello and welcome to my new podcast, Air and Space Stories. Are you ready for an exciting news? Fasten your seatbelts and enjoy your flight with me, Cinzia. This is the last episode, the number 10 of Season 1. In this episode, I will compare 3 sustainable solutions for powering aircraft engines. First, a look into the past. Kerosene was chosen as the ideal fuel for aircraft for several reasons, including its physical and chemical properties. Physically, kerosene has relatively low viscosity and density, which makes it easier to handle and transport than other fuels. Its low freezing point also ensures that it remains liquid at extremely low temperatures encountered at high altitudes. Additionally, kerosene has a relatively high flash point and low volatility, which reduces the risk of accidental ignition or explosion. And chemically, kerosene is a hydrocarbon with a relatively high energy content per unit of mass, which makes it an efficient fuel for aircraft engines. Kerosene also burns relatively cleanly, producing less soot and particulate matter than other fuels such as coal or diesel. This is important for aircraft, as it reduces the buildup of deposits on engine components and reduces the risk of engine failure. Now let's have a look at the sustainable aviation fuel, which is a type of fuel made from renewable sources that can be used as a substitute for traditional fossil fuels in aircraft. SAF can be derived from a variety of sources, including plant-based material, such as crops and waste vegetable oil, and non-plant sources, such as municipal, solid waste, and industrial waste gases. SAF has the potential to reduce the greenhouse gas emissions from the aviation industry, which is one of the fastest growing sources of emissions. SAF can help reduce the carbon footprint of aviation up to 80% compared to traditional fossil fuels. The use of SAF can also help reduce other air pollutants such as nitrogen oxides and particulate matter. While SAF is currently more expensive than traditional fossil fuels, the aviation industry has set ambitious targets for increasing the use of SAF in the coming years. The International Air Transport Association, IATA, has set a goal of using 10% SAF by 2030 and 50% of SAF by 2050. This will require significant investment in development and scaling up of SAF production facilities. Anyway, to use the sustainable aviation fuel in the aircraft, original equipment manufacturers, the OEMs, shall do some steps. First of all, certify the SAF on board their aircraft, because the OEMs need to work with the regulatory agency like the FAA or the ESA to certify this new type of fuel on the aircraft. And this involves, of course, extensive testing and evaluation to ensure that fuel meets safety and performance standards. Then they need to design the aircraft engines for the SAF. The engine manufacturers like Rolls-Royce or Pratt & Whitney, even if they have already certified certain engines to use the SAF, they should create an engine express for using this kind of fuel. This can include modification to the fuel injection systems, to the combustion chambers, and other engine components to ensure an optimal performance with SAF. And then, of course, a collaboration with fuel suppliers is mandatory because the SAF is needed in huge quantities, preventing every aircraft to use it, even on the engines which is already certified. And finally, OEMs have to educate the customers because they should push the use of SAF as a sustainable fuel to improve the state of the planet and to avoid or reduce or limit the climate change. As I said, there are already aircraft engines certified for the use of SAF, and more, of course, will be added to the list. For example, Pratt & Whitney, they have the PT6 engine. Rolls-Royce have other engines like the big one for the Boeing, like the 737, the Trent 1000 or 7000. Of course, Pratt & Whitney has the same certification for airliners like the A320, for example, the Bombardier C series. Then the General Electric has already certified the engine for the Boeing 787 and other aircraft. It's important to note that the specific SAF blend that an engine is certified for can vary depending on the engine type and manufacturer. Currently, there are already some aircraft that are certified to use the SAF, and this include, for example, the Beechcraft Bonanza, the Cessna 182, the Cirrus SR-22, and the Piper Malibu. This aircraft can use a blend, therefore a mixture of kerosene and SAF. Usually it's about 50-50 in percentage. Of course, the use of SAF in the general aviation is limited to the availability and cost. Therefore, it must be increased the production of this SAF in order to reduce the cost and cover the demand. As an alternative, many general aviation aircraft can also use unleaded aviation gasoline, which is undergoing its own transition to a more sustainable alternative. Now let's speak about the electric, what I call all-electric aircraft. I've done an episode about the urban air mobility in which I extensively covered, but I want to say that electric aircraft development is still in its early stages. There have been significant advancement in the last years, but the problem is related, as I said, to the batteries, because they can ensure so far short range flights, and they can be used therefore on regional and urban air mobility application. However, there are several larger aircraft that are in development in the all-electric segment that could have a significant impact on the aviation industry. For example, the Aviation Alice, the Manix Electric Cessna Caravan, an Airbus E, Fan X, Rolls-Royce project. There are many of them. Be sure to listen to my episode number 4 to have more detail. Regarding the long-range flight, it's difficult to predict exactly when batteries will be enough powerful to support this kind of, 1,000, 2,000, 3,000 miles of flight. And it's expected that technology will continue to improve in the coming years. Probably we'll see gradual transitions towards electric aircraft, with shorter range flights being the first to adopt the technology, and then longer range flights following as battery technology continues to improve. We know that Tesla is improving continuously the batteries, and sometimes it announces that a new battery, a bigger and long durable, has been produced, but it's not the only one that's working on this item. For example, there are a lot of industries in US like the solid power, quantum scope, agent technology, Oxys Energy, and also NASA is working on developing batteries for electric aircraft through its Advanced Air Transport Technology project. This is a great news, so let's see what's gonna happen. Now, it's the time to a look into the future. You know that fuel cells are a great topic when we talk about sustainability in aviation. First of all, a fuel cell is an electrical chemical device that converts the energy of a chemical reaction into electricity. Fuel cells are like batteries in that they produce electricity through a chemical reaction, but unlike the batteries, they can continue to produce electricity as long as fuel and oxidizer are supplied to the cell. The first fuel cell was developed by General Electric in the 50s for the space programs, and the first fuel cell was used to provide electric power and water for the Apollo missions. The one that sent astronauts to the moon in 1960 and 70s. And now the Artemis programs have the same aim of sending back the human being to the moon. Since then, fuel cells have been used in a variety of aerospace applications, including the UAV, the unmanned air vehicle, airships, and experimental flight. Of course, There are many types of hydrogen. The cleanest is the green hydrogen because it's produced through electrolysis, which uses renewable energy sources such as wind or solar power to split water molecules into hydrogen and oxygen. This results in a zero emission process as the only byproduct is oxygen. Of course, the type of hydrogen used in fuel cells depend on the specific type of the fuel cell and application for which it's been used. In general, the hydrogen used in fuel cell must meet certain purity requirements to ensure optimal performance and reliability. And of course, there are many methods for producing high purity hydrogen for use in fuel cells, including steam reforming of natural gas, electrolysis of water, and biomass gasification. The potential challenge with the widespread adoption of hydrogen in general, and especially for the green, is the availability and scalability of renewable energy sources needed to produce it. However, as the renewable energy technologies continue to advance and become more cost effective, it's expected that the production of green hydrogen will become more widespread. We have to remember that also electrolysis is powered by an external source of electric energy, such as battery or direct current power supply. This electrical energy is used to drive a non-spontaneous chemical reaction, which occurs at an electrode and electrolytic cell. In conclusion, we still need a primary source of energy to produce hydrogen or batteries, and this is the game. To be sustainable, we need to use other sources of energies that are not renewable at the moment, like the carbon. Anyway, in aviation, fuel cells can be used as a source of electric power for propulsion and other aircraft systems. Fuel cells have several advantages over batteries for aviation application. First, they can provide power for longer periods of time than batteries because they can be refueled with fresh fuel. And second, they have a higher energy density than batteries, which means they can store more energy in a smaller space. And third, they produce zero emissions because the only byproduct of the chemical reactions are heat and water. However, there are some challenges, as I said, to using fuel cells in the aviation. One of the main challenges is the infrastructure that required to produce, store, and transport hydrogen fuel. Additionally, fuel cells are currently more expensive than batteries, although the cost is expected to decrease as the technology improves and production volumes increase. Of course, we can use fuel cells on every type of aircraft, even on the smaller, because the dimensions can be adapted to the project itself. One of the advantages of using fuel cells in small aircraft is the high power to weight ratio, which is crucial for aircraft where weight is a critical factor. Additionally, fuel cells are quieter than traditional engines, making them an attractive option for noise-sensitive areas. So, in order to use the hydrogen on the aircraft, what shall the OEMs modify in order to apply this technology? First of all, they have to modify the aircraft structure to accommodate hydrogen tanks. For example, usually the aircraft store the fuel in the wings, while the tanks of hydrogen shall be accommodated in the fuselage. That requires a completely different design of the aircraft itself. And in addition, the aircraft's electrical and fuel systems will also need to be modified to accommodate the use of the fuel cells, because they need to be integrated with the aircraft's power management system, and the fuel cells will need to be connected to the aircraft's electrical distribution system. And most important, all modifications will require the certification by the regulatory agencies such as the FAA and the EASA, because they need to meet stringent safety and performance standards to ensure the aircraft is airworthy and safe for operation. One of the questions can be, are fuel cells equally efficient than kerosene empowering aircraft engines? The answer is it depends on various factors, such as the specific type of fuel cell and the specific aircraft application. In general, fuel cells are highly efficient at converting fuel into electricity, and they can be also more efficient internal combustion engines, such as those that burn kerosene. Fuel cells can also produce power with lower emissions than a traditional combustion-based system. However, in the case of aircraft engines, the energy density of kerosene is currently much higher higher than that of hydrogen, which is the most common fuel used in fuel cells. This means that kerosene can provide more energy per unit of weight or volume compared to hydrogen, which is an important consideration for aircraft applications where weight and volume are critical factors. That's why the use of SAF is the most intelligent and applicable solution for this moment. Finally, to conclude this episode, if you are wondering how the batteries or fuel cell power an engine, actually, the electric power generated by the batteries or fuel cells is used to power electric motors that drive the aircraft's propulsion system. I hope you enjoy this last episode of Season 1 about the sustainability for the aviation. I hope that you liked all episodes and that you will be there for the Season 2. Actually, will become available in September. Thanks for flying with me again. I hope you have a pleasant flight, and I would like to have you on board on the next season as well. Bye bye from Cinzia.